AICT ATAL Online FDP on AI and Simulation in Additive Manufacturing. Coming to his academic and professional background, Mr. Asim Anshul is a gold medalist from IIT Bombay in the field of material science and processing engineering. With 12 plus years of experience, he has collaborated with global OEMs and Tier 1 suppliers across industries such as automotive, aerospace, consumer goods, medical devices, and industrial equipment. Currently, he is a subject matter expert at Hexagon Manufacturing Intelligence, focusing on forming, joining, and advanced manufacturing technologies, process selection, material specifications and standards, failure analysis, and design validation of critical assemblies. Coming to his industrial contributions and expertise, he conceptualized and mentored various industry projects in India and globally. He actively works with MSME in additive manufacturing for process optimization, and he previously worked at ESI Electron Pneumatic and Hydraulic Private Limited and Bhushan Power and Steel Limited. Coming to his areas of interest, his interests are advanced materials and metal forming, joining techniques and CAE, additive manufacturing. With his deep industry expertise and applied research experience, Mr. Asim Anshul will provide valuable insights into the future of AI-driven additive manufacturing and process engineering. Thank you, sir, for accepting our invitation, and we look forward to his engaging and insightful session. Thank you, sir. Welcome. Now I will hand over session to Dr. Asim Anshul, sir.
Thanks, ma'am, for such a nice introduction. And it will be interesting to hear from our audience as well. I will prefer to make it as a more sort of an interactive one. And during my session, the wholesome objective would be to bring the importance of virtual simulation in the field of manufacturing. So, as a Hexagon, we are a solution provider for the industry in the field of virtual manufacturing on the various processes. Either it could be forming, either it could be welding or additive manufacturing. So considering the tone of the session, what we are discussing right now, we will start with how Hexagon caters the manufacturing industry in terms of providing the virtual simulation. We'll start with our solutions in the field of additive manufacturing, which will connect with the audience. And towards the later part of the session, we will move towards the role of virtual simulation in simulating aluminum forging and why aluminum is in forging simulations are important when it comes to simulating a manufacturing process, the criticality of aluminum being a material and so on. So this is something what we will roughly consider as a part of session. Just give me a minute so that I can bring some relevant slides on different line items. Okay. So I'd like to share my screen. Team, just let me know if you can see my screen. Hello. Anyone from organization?
Yeah. We can see your screen. You please continue. Okay. No issue.
Okay, perfect. So here, as I mentioned, that when it comes to Hexagon, we cater to industry in multiple ways. Either it could be in terms of design and engineering solution where we enable our industry experts in terms of establishing virtual prototyping for a different processes, like it could be a structural analysis. We have a solution called MSc Nastran. So the Nastran word came from the NASA. They predominantly use our Nastran code to simulate the structural load variation and all. Similarly, for the multi-body dynamics, we have a code called Atom solution. So yes, we provide our end user in terms of evaluating multi-body dynamics situation, and for that we have a code called Adams. Similarly, for CFD simulations, we have a code called the Cradle, which is historically a Japanese solution, and now it's acquired by Hexagon, and it's very I would say the entire Japanese industry is using Cradle for their CFD applications. In India also, we have a very strong customer base where various organization is using Cradle to simulate their flow dynamics. Similarly, for the acoustic simulation, like NVH parameter and all, we have a code called Nastran. So users are using Nastran to figure out the NVH parameters of automobiles. So industry like Tata Motors, Mahindra, or any OE are using our code to simulate the acoustic situation. Similarly, when it comes to material modeling, we have a code called DZMAT, and DZMAT is used to do a material modeling, how a material property is either metallic or non-metallic or even polymer. So nowadays we have a new amount of research going on with material modeling. So how those materials can be designed in terms of required properties to suit the application and all. And then comes the final one as a manufacturing process simulation, which we are going to talk majorly today. And it includes VMC solution, virtual manufacturing and caustic solution, where we are going to talk about the simulation of the forming process, simulation of welding process, and simulation of additive process. So this is something what we can simulate in terms of manufacturing processes. Now we talk about that when it comes to virtual simulation, what all we cater to industry. So first one is regarding early design stage, means a designer for any organization. On the right hand side, you can see that these are the multiple verticals, like at the design stage they should be using at, or the proto stage where we talk about the physical trials and all, so there they can use the solution. And then it comes to the production stage, means the final production is running on. And then the last one is on the quality stage, means quality inspection, how the part is, whether it meets the required quality or not. So these are the few major applications what we counter for the virtual simulation. So when it comes to university users, so our users are mostly hired by these our customers for these verticals, means say tomorrow if you goes if we have students as an audience, so tomorrow if you got a job offer from Maruti. So there you might be doing some design related work, or you might be a part of proto team where you have to be involved on the physical tryout side, or on the production side. You might be working on that, how to improve the production, or you will be hired for the quality role where you might be working as that what should be the ideal quality of the component and all those things, whether it meets the requirements or not. So these are the few roles what you are going to do it tomorrow. And there comes the virtual simulation, which will enable the young user in terms of doing a virtual setup and realizing that how things will respond in the reality without doing any physical prototype. Say, for example, tomorrow, if you are going to work on the software, with the help of software, you will ensure that, say, for example, you are going to work on a 3D printed component. So right now you can see on the top and side, as a user, you can run the simulation and then you can figure out that when it comes to powder bed fusion application, what should be the size of the powder, what should be the size of the layer of the powder, with what velocity we should be depositing it. Do we really need a preheating temperature for the base? Do we really need any sort of support structure to print that particular component? Do we really need a orientation analysis? What should be the ideal nesting for the base plate in terms of getting a maximum productivity out of that? So those things can really help you. So right now, the practice is, the conventional practice is that people will do multiple physical experiments, and lately they will realize that no, this is not a right way, or no, this is not a right way to print a component, not to support this component. So eventually they burn their hand with the multiple physical tryouts, and then they will learn that how we can get into the printing of that. So now the route, what we are offering to the industry is that with the help of virtual simulation, they can do some experiments, they can do all sort of these kind of permutation combination virtually in our software, and then they can cater to the shop floor by doing first time right kind of approach. And right at a first time is something what we talk about, and right at a right time, because industry has a huge demand of meeting targets and all those things. So that is the whole and soul of the offering what we have as a hexagon solution. So this is how it works. This is how we cater to our industry. This is how we offer support to our industry. I hope this had given a rough idea on that, what is the role of virtual simulation in this particular industry, and those things. So now coming back to that, what we offer to our manufacturing expert, meantime to the organization, can you just add on those guys in that? Because I can see multiple notification on my screen, which is a bit disturbing. So please add on those the people who are in the lobby. Meantime, so now we when it comes to offering a solution for the manufacturing, we have four verticals when it comes to virtual manufacturing and costing. The first vertical talk about the forming simulation. The product what we offer to the industry is Simofact Forming, where we talk about all sort of forming operations like cold forming, hot forging, sheet metal forming, mechanical joining, rolling, ring rolling, open die forging, heat treatment, and pressure welding. Similarly, when it comes to welding applications, with the help of Simofact welding, you can simulate for the processes like arc welding, laser beam welding, electron beam welding, brazing, RSW, and whatnot. The D is something what might be exciting to the people who are working on additive manufacturing. So there are institutes who are effectively using our modules for the both solution for DED and additive manufacturing. So we have a strong user base with IIT Madras. We have a strong user base with IIT Hyderabad. We have users in IIT Bombay as well. Similarly, in the north, IIT Roorkee and all other institutes are effectively using our manufacturing simulation to do their research, to support the industry in their capacity. So similarly, for the sheet metal and costing, we have a solution called FTI. So this is something how we align our engagements. This is something how we are aligned to the industry, and effectively we can talk about these engagements. But for today's session, I will start with the Simofact additive, and somewhere I will end towards Simofact forming. In between, if you have any queries, just do let me know. So at this note, I would like to start with Simofact forming. Sorry, Simofact Additive, where we talk about the solutions for additive manufacturing industry. Meantime, Zubair and organizer, how we are taking Q&A? Is it going to be towards the end of the session, or we can take a pause after additive manufacturing session? We can go for the Q&A, and then probably we can move for aluminum forming. So how you guys will recommend?
Actually, the Q&A section will be there at the end of the session.
Okay,
So
okay.
if anyone having their own doubts, they can raise the hand, and they can switch on their mics because everyone is allowed to switch on their mics. So there is no issue.
Okay, so instead of switching on the mic to avoid the chaos, I will prefer, if you have any queries, you just drop your queries on the chat box. So that can help us to read through it, and we can, at different stages, we can take a pause and then we can read out your queries. Okay, so now I'm going to start with the manufacturing as it suits the tone what we have for this particular session. So when it comes to additive manufacturing process, Hexagon provides end-to-end solution towards that. So we start with the simulations of additive manufacturing process. We have tie-ups with multiple players who can support you on the production of that 3D printed component. So we have our relationship with different organizations or machine manufacturers who are working in the field of 3D printing. So we can connect you with that. And then when it comes to quality inspection, if you recollect the slide what I presented on the different spread of hexagon, that we cater to the metrology also. So we have a solution in the field of quality inspection also, where you can work as a reverse engineering model as well. So we have a solution for the quality inspection, and then the service life modeling. We will see in some slide that if you have a free printed component, how you can assess the quality of that component. So this is how we work. Similarly, what all process we can simulate for? So the process what we can simulate is the powder bed fusion, metal binder jetting, DED, FDM, and SLS for the non-metallic printing. But I must say that industry or the researchers are mostly using Simofact for the first 3 engagements, as the metal printing is very costly. The risk for that printing is quite heavy, and there is a possibility to lose a good chunk of money for the owners in metal printing. So these things can be done. And now when it comes to FDM and SLS, we have solution as a DZ-mat additive manufacturing, where you can get into the plastic printing process and so on. So this is something how we are oriented ourselves. Just to start with the case study, what we are doing here. I'd like to bring a case study for Hero Motocorp. What we have engaged with those guys. So here the process starts with that at Hero Motocorp, they identified that what could be a component which for the additive manufacturing process. So for example, they pointed out that let's print this particular component. The thought process was that this component has some X amount of weight in a vehicle. when it is going to be manufactured from a conventional manufacturing process. Could be casting, could be forging, whatsoever the process. In this case, the conventional component was casted. Then their team worked on a way that they figure out that what could be the optimum design for this particular component, which means that they ran our solution for design for additive manufacturing. They optimize the design parameters in terms of weight reduction and all those things. And once they have an idea that let's reduce the weight of this component by 50% with a particular design, with the help of additive manufacturing process simulation, they ensure that this can be printed effortlessly with the minimum of a scrap in a particular way. So with the help of SimOfact additive manufacturing process, they simulated that this could be the ideal orientation to print this part. This could be the ideal support structure to print this part. Once that simulation is done, they ensure on the process parameter, and eventually they move towards the durability analysis. Okay, means once we are done with the choice of the component, they ensure that that particular component should be printed in this way. Then they move to the next segment, that the component what we are coming with a new design, it is going to meet the functional requirement of the conventional component. So for that, a user can run the durability analysis with our fatigue based software, and then they can figure out that with the new design there is no compromise on the performance of the component and all, and effectively we can reduce the weight of the component by 70%, 60% and all. So this is a wholesome story which end user can percolate with the hexagon solution. Either on the design side, means selecting a conventional component and then optimizing the weight for that. Then moving towards the manufacturing of that particular component. What should be the ideal way to manufacture that component? And meantime, meeting the quality requirements. So this is how we work and we respond to that. So now we have different modules to study those 3 line items. So one is Apex GD, generative design, which will help end user to optimize the design of a particular component. SimOfact welding, one can do the DED simulation, and then comes the powder bed fusion simulation. So this is something we can do. Now I will start with the generative design. So yes, you can see that on the right-hand side, we are going to start with a conventional component in this particular software, generative design software. So probably tomorrow you are working with as a consultant to a particular industry. We will consider a particular component, that how to start designing for that. So here Apex generative design software will help us to do a weight reduction for that. So now you can see we are running generative design in the background, and now you can see that in a software we will assign that we are looking to do a weight reduction by 50%, 60% and 70%, and depending upon the requirement for the weight reduction, the solution will provide you an alternative design concept. And now you can take this design concept, you can make sure that what is the going to be the manufacturing process for this with the printing simulation, and then finally you will ensure with manufacturing stresses whether it will sustain the required performance or not. So this is how we are aligned in terms of optimizing the design to the performance. So here you can see we are sorry for the abrupt orientation, but you can see that we are starting with a conventional design and we are ending at this particular point. Then you can simulate the process, you can figure out the stresses, and you can figure out the distortions, and then you will come with the right design, right manufacturing processes, and so on. So yes, what we can achieve with the link up of the solution, weight reduction, fixation points, efficiency of the printing, the cost of the printing. Just give me a minute. My power is going on for the laptop. Just give me. So yeah, this is something which is very much exciting in nowadays, and there are researchers who are going to be hired by industry in this particular line. So yes, this is all you can explore with this. Now on the simulation side, I will start with some processes. Just give me a minute. Meantime, please feel free to drop your yeah. So I'm resharing my screen. Okay. So yeah, we'll start with laser powder bed fusion. So currently you can see the printing process, what we have in the reality. Though you can see the recoater is moving with the laser, doing the printing operation. And again, the reprinting, and finally you have the components which are going to be removed out of that list. And then you can see this is the process in the reality, and same thing we replicate when it comes to the simulation. Similarly, for the metal binder jetting also, we have different processes. Here we have a very hot spot coming from the centering. So what should be the centering process parameter and all those things we need to simulate here. So yes, these are interesting workflows which can be simulated here. Similarly, for non-metallic printing process, we can simulate different stages like topology optimization by different weight of the polymer and all. Then comes the material engineering, what should be the fiber reinforcement, the shape of fiber, and all those things we can simulate. Then there comes the process simulation, then part performance, and then the inspection. So end to end for the non-ferrous processes we can simulate. So here, sorry, I was able to hear something. Any doubts? Anyone having? Okay, so now just to brief you on the route what we can simulate. So it starts from the design and engineering, where we talk about the part design. I have just briefed you on that, how a conventional component can be studied in this particular process, and how we can figure out that particular component whether will meet the requirements or not. So this is something what one can do with hexagon DFAM. We call it as a design for additive manufacturing solution. So yes, this is something what we can simulate as a deformed process. Uh, this is something can be done as a deformed simulation. Similarly, now as a user, when you move towards the next step, we are going to talk about the type of process, whether job preparation is right, whether the planning is right or not. So these things we can figure out with the help of our virtual simulation from Simofact. Then as I mentioned that we have tie-ups with machine manufacturer, could be MAs, could be SLM solution or other mix. So we can connect you to the right guys and you can establish your lab and all. Then once your real-time printing is established, then it comes to the quality inspection, whether the part which is printed is right or wrong, whether it is correctly printed or not. So these things can be studied out with the help of our solution. Then it comes to, just a minute, guys. Am I audible? Can you just confirm?
Yeah. You're
Yeah,
audible,
okay.
sir. Please continue.
Okay, and then with the help of our hexagon metrology solution, you can do such inspection and all. We can help you to establish your metrology lab as well. The required CMM machines and all. Just a minute. Actually, I'm at a public place, so you might be getting some noise from the background. I'm request. Yeah. So here then comes the service life also. You can do service life analysis. We have seen that CA fatigue and all those kind of engagements. So just to give you a rough overview that what we can do here. So the rough overview is you can start with a conventional component and then you can work for the different candidates for the design. You can go for the performance analysis. Then you can go for the printing analysis. And again, with the manufacturing stresses, you can print the component. You can assure the things and then you can move forward. So the point which we want to highlight here for your notice is this particular part, condition. We are starting with this particular component and we are ending towards this particular component. Just imagine the amount of weight you are going to help your team to reduce, and eventually you are going to be consumer for that component, or a vehicle. So you just see that the moment you are reducing the weight of the assembly, you are going to make your help your organization to make the vehicle more efficient, fuel efficient, carbon emissions. So those objectives, what modern day industry is looking for, we can help them to work on that particular line item. So this is the impact what a simulation can bring to the manufacturing industry. So I hope you guys are through with this, the role of additive manufacturing, the role of virtual simulation to that, the role of DFAM to that, role of simulating for the candidates manufacturing process, the fatigue properties for that. So now I'm going to bring certain case study for your reference that we are starting with the printing process. You can figure out that how the distortion, what should be the ideal support structure for that. Say, for example, you can do a setting and then you can figure out that you have 3 design candidates and then you can run the simulation. You can figure out that out of these 3 design candidates, what is going to give you a right piece of component, either in terms of distortion, either in terms of residual stresses. So, and on the basis of those virtual runs, you can select your component. So now I'm reaching to a very interesting segment where you can help the organizations in terms of figuring out the problematics of the printing process. So now with the help of Simofact additive manufacturing process, so till now, just to refresh you that we have discussed about the role of a DFAM, Design for Additive Manufacturing softwares, to convert a conventional component in an additive manufactured component. Now we are moving towards a point where we are going to establish a fact that how additive manufacturing process simulation can help our end users. So first thing is to establish the part printability. Whether the part is going to be printable rightly or not means what should be the ideal process parameter, the laser heat input, the choice of machine, the bed size, those things can be figured out on the basis of the simulation. The cost of manufacturing, time of manufacturing, you can figure out the support structure, the number of component, which we call it as a nesting in additive manufacturing terminology, the choice of the component layout and all those things with respect to the distortion and the residual stress. So for example, this is a coupon-based printing, and here you can see after printing and once the component was cut out, you can see the huge distortion in this particular location, which was reflected in the real-time data also. So those things we can figure out. Similarly, when it comes to the manufacturing risk assessment, you can simulate for the recoater, blade connects, shrink line processes, part failure, crack analysis, support structure, delamination, and also those things you can figure out. The image is giving you a rough idea that in the real time, you can see that the crack was assessed. In the simulation, also high residual stresses were traced around that particular area. So this is something what we can simulate. Then comes the process optimization, like what should be the build orientation, support structure. So those things. So these are the real-time problems. Just give me a minute. Hello. Yeah, guys. Sorry. Yeah. So we were talking about the risk of process optimization, and then finally it comes to the post-build operation. Like once you have done the printing, you are going to do the post-print operations like heat treatment, the microstructure analysis, and all. So those things can be better studied with the help of this. Okay. Sorry. Okay. I don't know. Yeah. So now here you can see SimFact defect analysis. So we can simulate the defect analysis of the additive manufacturing process as well. You can go for a kind of fusion we are having, whether we can get into balling effects, you can effect of excessive keyholes and defect-free melting, and also these kind of process you can simulate with the SimFact additive. The only thing is that you need to understand that what is the right material. You need to model for the material, and then you can simulate for these processes. So these are the beauty of simulation. At this note, I'd like to take a pause. And please do pop your queries in the chat box if you have anything on SimFact additive manufacturing process simulation. So just do let us know on that so that I can answer your question towards the end of the session. Now I will be moving towards the next segment where we talk about the aluminum forging and all. Nowadays, you know that weight reduction is a significant agenda for that. So now we are looking to optimize the weight of a component. Say, for example, automotive industry. We know that higher will be the weight of the vehicle, the more fuel it requires, more carbon emission, and all those things. So industry is looking for the weight reduction, and nothing can beat aluminum in terms of replacing steel to its strength to weight ratio or whatever be. So just give me a minute. I'm trying to check my slides. Okay, guys. Sorry for delay. Finally, I got that, which I'm looking to present. Yep. So now coming with aluminum forging with Simofact, and we call it as a forging before the reality because if you're doing real-time experiments, you are going to know that what will be the outcome of your process and all. So now this is something I was discussing, that why aluminum forging. We talk about the requirement of aluminum. Now demand for aluminum is shooting like anything, the different reasons. So even to be honest, that if we compare ourselves with the powerhouses like Americas or the China or even the Europe, we are lagging behind in terms of implementing aluminum as an alternative material. The On a global level, the production of aluminum is increasingly huge compared to what we do in India. So now Indian government is also looking serious towards that particular segment. If we compare with the China, we are on a lower side, but there are multiple data which says that the role of EV is significant in terms of promoting aluminum as an alternative material. Similarly, for the solar panels, you can talk about that packaging with the aluminum. So these things are exciting one. Then comes the aluminum as a material, what you can figure out as an alternative. We talk, yes. Then comes aluminum forging. It's very important when it comes to working on the aluminum, because the forge components are too bulky, and those are the hot target when it comes to segregating that what could be means forge components are the right candidate to be replaced with the alternate manufacturing process, alternate design, or alternate material. So yes, a forging industry is adapting very seriously towards the new trends for the aluminum forging. So yes, this makes aluminum forging is quite imperative to study the aluminum forging. It's quite imperative. The good part is the means when it comes to virtual simulation, compared to the steel, in the reality, in aluminum forging, there is not too much of database ready with the current manufacturers. So they have to rely heavily on the virtual simulation to see the response of the material, how it's going to flow, what will be the grain orientation, whether it's going to be too much congestion around that. So those things, virtual simulation can be help you. So yes, this is something why we should be doing aluminum forging simulation. So now in this segment, we are going to check that why aluminum forging before the reality, though why forging simulations for aluminum is quite important. So yes, when we talk about the aluminum as a material, we all know the criticality for aluminum lies with its property. The properties of aluminum are temperature sensitive. The properties like thermal conductivity, the melting points, and all those things. So this makes aluminum as a sensitive material when it is subjected for hot forging, because as a user, we are used to of managing steel. When you go to the shop floor, due to the steel properties, the shop floor is experienced to deal with the steel. But when they have to adapt aluminum as an alternative material, they are not very equipped, or their learnings are not that much to adapt aluminum for their shop floor. So now they have to rely on the virtual simulation, that how the modeling of that aluminum is important. What will be the heat flow rate? What will be the temperature drop as a function of time? How they should manage the heat content of the aluminum for the forging operation so that they can meet the load requirement? What should be the ideal strain rate in terms of forging aluminum at sensitive temperatures and all? So those things becomes quite crucial, and their virtual simulation is, play the role. Then comes material flow behavior, like how the microstructure will respond, the grain flow, and all those things, because the aluminum has a different flow parameters compared to the steel. Then the die wear for the forging, because with the aluminum there will be too much of friction and all, because aluminum being a soft, dies material are coming from steel. So due to the difference of the hardness and all, it becomes critical. Now the oxidation properties, like you know that aluminum is exposed to oxygen and then Al2O3 and all those things. Then the complex shape, whether the aluminum flow parameter will ensure those complex shape and all. So these are the few criticalities with the aluminum forging. And now with the help of virtual simulation, you can meet these requirements. You can test the flow of the aluminum. You can test about the temperature, flow rate, and all those things. And with the help of virtual simulation, you can meet these the requirements that what will be the ideal temperature and at what temperature we should force to get a proper fluidity in the aluminum and hot forging operations and all. So now I'm just going to bring one case study coming from the Mahale for the aluminum piston. So as a process, these were the operations for the aluminum, like the challenges what we have. So the component was a thin wall component. Transition between less material and certain profiles were very critical. It was in a near net shape operation, like the slag was not much, the flash volume was too less in this case, die wear and the die crack. These were the operations starting with the slag. So now when it comes to simulate the process, we start with the creating a material data. We have a library. User can select a material from the library, defining the press parameter, like what should be the choice of the press, whether it should be the clutch press and all those things. Then comes the tool data, like what should be the die, what should be those things. Then you can model this as a process. Then you can simulate in this flow, like what will be the material flow, the forces requirement, the crack formation, whether we are going to have a crack or not, tool analysis, what will be the tool life, and then the microstructure. So in a rough note, you can make out that these are the outcomes we can run through the simulation. So now what is going to be the material flow? It is going to be governed by the flow defects, mold filling rates, and the geometry. Similarly, the forces and all movements can be established with the aggregate of the selection, the choice of the machine. Then comes the freedom from the cracks, the crack assessment and all those things we can figure out. And then comes the tool analysis, what will be the tool life and all those things we can figure out. And then comes the microstructure, like a kind of grain size, phase, proportion, and all those things can be figured out. So just an example, I'm trying to bring here on the load calculation. So now you can see that these two cases for in forging, there were multiple stages. So upsetting and then the final forging. You can see the blue color means these are the areas which are under filling process. So initially, the load was on a lower side. Lately, when the filling was on a red color means it's filled, means the profile has reached. So the moment we are getting close to the proper filling, you can see the load calculation, loads are increasing. So those things can be figured out. Then comes the fold detection and all. So you can simulate for the fold detection. Here you can see with the help of simulation, you can figure out that these are the hottest spots where you will have the fold and all. So now here you can see the die life analysis and all those things. So you can simulate for die life and all those things with this. Sorry, just a minute. Just give me a Yeah, so you can figure out the deflection in the dies and all those things. We can make out with the help of these virtual simulations. You can figure out the hottest spot where a die could be susceptible towards the crack and all, considering the load, extra load, what we are getting on the dies. So yes, these are the study what we can perform here. from the die life to the die load to the material filling and all. So those things we can figure out with this. Now, why we need virtual simulation with Simofact? So there are key differentiator when it comes to Simofact. So in Simofact, we have finite volume kind of approach to model out hot forging process. So yes, as a user, one can simulate for the finite volume process, and you can figure out that how material is flowing. You can see the mesh pattern for the volumetric analysis and all those things. In Simofact, you can figure out the fatigue life of the component and all. So that can help you in terms of assessing that. Uh, uh, just Then comes the material modeling. So we have a very much rich library where user need not to invest their time to build a material like other solutions. So here, as a user, you can select a material either for the additive manufacturing process or for the welding process or for the forging operations. So you can select a material and you can run the simulation with your material. So here for each material, we capture the temperature dependent properties, we capture the mechanical properties, and that really help us to model out the particular process. Now, to the other operations like estimating the piping defect and all. So you can see that with the help of simulation, you can simulate for the piping defects and all those things. So yes, this is the beauty of virtual simulation. Say, for example, in this case, during the course of forging, users were getting these piping kind of defects. So now, first thing first, what they did, they ran for the simulation and they replicated the same thing in the simulation as well. Now, as an alternative, they work out on the alternative solution for this kind of piping defect. So initially they were, if you look at this, it was more sort of a reverse extrusion where the flow of material was in a single direction. And lately they changed the design of the forging, and then you can see they put a extra cushion of the material in this case, and then the downward flow of the material helped them to control the piping issue. So this goes in that way in terms of how simulation can be implemented in shop floor to get the real-time issues and all. Now, same thing can be assured with the fold formation, fold assessment and all. So we can again implement the simulation to figure out that what will be the role of simulation in terms of estimating the fold and all. Now you can see the real-time examples where you can see there were the folds in the real-time samples. And when it went into a simulation, you can see that a mesh view of that particular component. You can assess the fold and all. So these things are very, very important when it comes to aluminum forging, because you can make a, as I mentioned, that there is no ready-made data available for the shop floor guys to troubleshoot these issues. And there the simulation and the new experts come into a play, and then they can provide the solution for the industry in a first time right kind of tones for this. Similarly, weight reduction involved in that. So these processes can be done out. So now estimating the issues with that. Now, at this note, I'm going to converse to a point where the conventional processes and the additive manufacturing are coming on a single platform. So now in the beginning, we talk about the additive manufacturing, and now when we talk about the forging process, nowadays we are talking about to bring out the punches for the folding process with a new design where we talk about the cooling channels, maintain the temperature of the forging punches at a particular level. And there, these simulation with the Simofact for the forging process and additive manufacturing process can help end user So there, as an end user, you can simulate for the stresses coming out of the additive manufacturing process. You can use those punches to do a forging operation and figuring out that what will be the life improvement for these newly conceptualized punches through a additive manufacturing route rather than going with the conventional casting punches. So these are the certain benefits what we can drive through this, and now you can work out on that. So yes, this is something you can see eventually industry can receive from simulation of the process. They can save cost of the material, they can save the cost of the process, they can save time to develop that particular component, and they can meantime enhance the quality of the product as well. So this is something as an end user one can receive that. Now again, coming to this slide, as I highlighted that in Hexagon, you can talk about the different levels of engagement with the manufacturing industry, different levels of engagement with the designers, different level of engagements with the shop floor guys. So for research and in academic institute, we are seeing a huge amount of inquiries coming for our first line item, which is on the design and engineering solution. For industry, we support academic institute with very attractive academic packages and all. So probably an institute can get into or enroll themselves for such packages and all to get benefit of the virtual simulation to enable students to get in touch with the real technology and the trendy technology as well. So there are a few benefits what institute can drive from our academic packages and all. So if some students who are interested for the research in a similar field, we can help them on that. So this is a rough note. At this note, I would like to end my presentation and will be open for the doubts and the queries. Do let me know if you have so. So guys, any queries?
Session is open for question. If you're having participant, if you're having a question, please ask.
So yeah, it's bit late. I can sense it.
Asim, I have some question.
We'll take yours towards the end, Zubair. Any other one?
Just basic. Actually,
Yeah.
the SIMUFAC, na, this material behavior modeling.
Yes, yes, yes.
Material behavior modeling particular to the high temperature forming process or like some other, previously we know about the CISWELD welding joining process.
Yeah.
So how does SIMUFAC handle this one? Exactly.
So yes, as a material, we have the material database which is coded with those properties. So we have different material equations. We follow that. So simple, say for example, temperature dependent load response. So in in material we have covered out for that, like for 20 MnCr5 as a material. So we have modeled it for temperature dependent properties, like at room temperature, what will be the stress sustain curve for that? When it goes to 200 degrees centigrade, what will be the stress sustain curve? At 800 degrees centigrade, what will be the stress sustain curve? So as a user, you can use this and then you can model it. Okay, if you are doing the forging at that temperature, what will be the load requirement? If you are forging at a lower temperature, what will be the load requirement? Similarly, when it comes to the cooling or the heat treatment process simulation, we model for the CCD diagrams, and also based on the cooling rates, eventually you will make out that what will be the metallurgical phase coming out of that heat treatment process, whether where you are going to have a palatic phase, whether you are going to have a benitic phase, whether you are going to have a martensitic phase. So such sort of analysis you can figure out with that. If at all you are going to have a mixture of multiple phases, so what will be the proportion for that? So those equations are coded with all the materials what we have, and based on the response for the environment, as a user, you will get the output.
Okay, like constitutive equation models means in case of
Sorry? Sorry, can you please come again?
constitutive model means like Johnson-Cook equations.
Ah,
We
yeah,
have no maybe
yeah,
that
yeah.
one.
Johnson Abraham, Johnson Cook. So yes.
So with this combination, we can do the metal forming process completely. Am I right?
Yes, yes.
And but how the calibration of metal properties would either from experimental data like
Yeah. So for
metal database
example,
factory you have.
you have a past experience with the welding. So for example, if some user is running a welding process, so what we do on the calibration side, we will select a material from our database. We will compare it with the real-time welding parameters, and then we will do a calibration exercise that in XYZ direction, what is the distortion for that particular material, how close it is with the reality, and then we will do a calibration for that. Similarly, when it comes to additive manufacturing, we do calibration process like in XYZ direction, what is the strain value, and once the calibration is done, we will go through the printing process.
Like for automobile and the aerospace industry, aluminum is one of the most demandable material. So for these new materials, since it is under the research, so many aluminum they are modifying by some automotive industry or ISRO, NASA, like these kind of. So for these kind of materials, because by default there is no metal
Yeah,
property,
so
no?
now you brought an interesting point. So the one thing what we expect from the user that yes, the commercial grades or the commercially popular grades are available in our library, and if somebody is looking to look for the output, one can simulate for that. Now the people who are working on the material research, so there comes the academic implementation where probably you can work for the temperature dependent properties, how those strain values are there. So we have a list of property what a user need to create for a material. Now, as a user, what we recommend that you can do physical experiment with your advanced material or a new material who could be an alternative for the conventional world. Then you can create the database for that material, and then you can implement simulations to figure out the response of that material to the real-time printing situation. And then probably you can advocate for that particular material that let's use this one as an alternative for other aluminum grades. So this is how people are doing research in the field.
What about from the AI point of view, like Simufed can be integrated with the machine learning algorithm to optimize the
Yes.
manufacturing process parameter?
So we have implementation at VSSC for G codes and all, where we are working on some DED process. So yes, it can be implemented.
Yeah, very good evening, Asim. This is
Yes.
Dr. Preetham.
Very good evening.
Yeah, I have a few queries are there.
Yes, please.
One video you have shown that laser powder bed forming.
Yes,
In that, after having the mold of that equipment, it used to taken out. During that, any effect of temperature is there in that processing?
Yeah, of course, that at what temperature you are going to take out, at what temperature you are going to cut the component from the base plate. So yes, what we have seen that temperature plays a role in terms of distortion. Means say if you are cutting at 400 degrees centigrade for a steel grade, And
Is
if
it
you are
based on the,
cutting,
is it based on the material? How, like what kind of material we are using for the manufacturing for that process?
yes, yes. So
Based
for
on that,
aluminum,
temperature will vary.
yeah, exactly. So
Okay.
material and the design also, and whether if the design is robust, then you can cut it at any temperature. It doesn't play a role. But your support structure is sensitive, then cutting at lower temperature is something we promote. So there are multiple factors. It's not thumb rule sort of that if we are choosing this material, we should cut it at that. Support structure plays a role. Then the base plate temperature plays a role. So there are multiple variants which plays a role in terms of deciding that at what temperature we should cut the sample.
Yeah, thank you. One more question is there. In that Simfact building, that solidification and phase transformations model, like different materials you are taking.
So on the solidification, let me touch that part. That when it comes to solidification, it comes to a CFD side.
Okay.
So it's a so when it comes to Simfact welding, we talk about thermomechanical process assessment. We don't get into the flow side of that welding process. So there we have, I would say that we are mostly into the thermomechanical side of the process assessment, where we talk about the heat input, where we talk about the outcome of that. And in this process, we are going to talk about the distortion coming out of the welding, the stresses build up coming out of the process, and then the metallurgical transformation coming out of the process. So we are into that side. We don't get into the solidification side. I hope I gave you.
Yeah, thank you, thank you. Yeah, I got it. Your point. Like both are in different ways. One is like design and simulation side. Another one is CFD, like the fluid parts, how the fluids are moving in that. Maybe in that kind of simulation, you are doing both things.
Exactly.
One more is there, like you are using the DFAM software also, I think.
Yes.
Yeah, like in the DFAM, is it like varying from any other software like CFD we are using for the simulation purpose? Again, FAME also one of the part of that. Again, DFAM, any difference is there in that compared to the others, like how it is working?
So when it comes to DFAM, we have a solution called Apex ZD for DFAM. So this is a dedicated module meant for the additive manufacturing process. So there are generic solution, means they can talk about the topology optimization. But generative design is a different subject for additive manufacturing. And the solution what we offer is in sync with the additive manufacturing. And that makes it a bit different from the other existing code.
Okay, so there also coding is possible, like separate coding you can write and you can implement in
Yeah,
that.
you can do that. You can do that.
Yeah, that is very easy.
Okay.
Yeah, thank you.
Great. So, Preetham, we can connect later also if you have any queries. Thanks for the interest.
Definitely.
Audience, if you have any question, participant, please ask your question.
Okay, so the chat box is not allowing to drop message.
Actually, question answer one part is there. There they can enter their queries.
Okay, but I'm not seeing the permission to write anything. I'm not sure. You guys can write.
In chat box, question answer session, you check one there.
Okay. Anyways, any other queries, team?
Participant, if you're having any question, please ask, or you can put in the question answer session. Sim, someone is asking, can you share your PPT after your presentation?
I can look into that. You just write me a mail. I will do the needful in this case.
Okay, participant, I will ask the email ID. You can share if some other features, some questions are available. You can ask him in email also. If participant, if there is no question, someone's typing. So, Bita, you want to ask some question? Your voice is not audible. I think some error. Okay. If there is no questions, then I will say out of thanks for this session. It's my privilege and honor to extend an heartfelt word of thanks at the conclusion of today's informative and engaging online session by Asim from Hexagon. And I would like to express my deepest gratitude to our esteemed speakers, IIT Bombay, Dr. Gurminder Singh and Mr. Asim, for sharing their valuable knowledge, insights, and expertise. The thoughts provoking discussion and have truly enriched our understanding for the subject, and it really inspired us all, I hope. And a special thanks to all our faculties, our participants, researchers, and professionals from various prestige institutions across India. Your enthusiastic engagement and some questions and active participation have made this session really great success. Finally, I thank our institution, Aditya University, FDP, ATAL, AICT portal for their continuous support and for making this learning opportunity possible for us. With this, we conclude our today's session and we look forward to our participation in the upcoming tomorrow evening 6 o'clock session. Thank you, Asimji. Thank you so much.
Thanks, Dr. Zubair. It was nice connecting with you after a long time. It was a great opportunity for me to pass the knowledge to the new set of students, whomsoever the researchers, and you can reach me out on the LinkedIn. You can reach me out with the mail and phone details from Dr. Zubair. I will ready to support you in this transitional journey where you can see the simulations are going to be have a path-breaking thing with latest manufacturing trends. So looking forward to meet you on the other side. And bye-bye, good night. Bye, team. Thanks for the opportunity once again, Dr. Zubair and the Institute. Bye.
Thank you, participant. Now I'm going to end the session. Now you can log out. Thank you. The feedback link will be provided soon in WhatsApp group.